Welcome class for the test 3 pretest YouTube video. This test goes by question of how the test will look like. The pretest this time did not, that was handed out, did not look like the format that the test will be in. So I decided to make this one so that way we're all on the same page. Okay, so at the beginning, you're given a time versus position table. So here's the table, a time versus position table. And then you're asked to, first and foremost, show that you can analyze it. So the idea is, I can analyze the motion of an accelerating object using position and time. So what we've done in the past with the previous unit, we just went over at a constant rate. Well, this object isn't at a constant rate, it's an accelerating rate, meaning the speed is changing, it's not the same. The previous ones, we had a consistent speed, so it was a predictable speed. So this one's going to be different. So we need to make a position versus time graph that indicates that. So how will we do that? Well, remember, guys, let's figure out how many places we have and what we're going to. I'm going from 0 to 144. I'm probably going to want to go up by 10s. So I'm going to have 15 dashes. You know what? I might even make that, I honestly might make that up by 20, so that way I only have 7 dashes. So let's do this. I'm going to start with a line here and another line there, and I got to label it, right? So this is going to be the effect of time on position. Remember, that's how we do this. We did this independent over the dependent. So this is going to be time. It's going to be in seconds, right? And so I'm going to go 1, make this bigger, 2, 3. Let's get this out of the way so we can see this. 2, 3, 4, 5, 6, 7. Now it probably wasn't drawn to scale, but on your test you'll have that. So this is time in seconds. The next thing is there's position. It's in meters, so I'd put position in meters. And we're going to go up by 20. That's probably the best for us. We're going to go 0, 20, 40, 60, 80, 120, 140, 160. Okay? And let's make our data points. So the first one is 0, 0. I'm going to do a different color now. Let's go 0, 0. The next one is 1 and 4. 1 and 4 is going to be about right here. It's even smaller than that. Let's make that smaller. So 1 and 4, and the next one is going to be 2 and 16. So 2 and 16. Oh, that moved across it. So let's move this picture down. Okay. 2 and 16, and then it's going to be 3 and 36. So 3 and 36. The picture keeps moving on me. So 3 and 36 right here. And then 4 and 64, so bring this 4 up all the way to 64. And then 5 and 100. Oh, I messed up. So let's make sure. I'm glad I caught that. So let's go get this fixed because I messed up. If you guys were watching the video saying, Mr. Arnold, you messed up your scale. I sure did. Let's get that fixed. That's 100, 120, 140, and 160. So 20, 40, 60, 80, 100, 120, 140, 160. Okay, good. So let's go 5, 100, and then 6 and 144. And if we look, okay, now let's connect these lines. Oh, that's a terrible picture, so that's a terrible color. Let's get a different color. Okay. Close that. So here we are. Okay, so look at this right here. So I can analyze the motion of an accelerating object using position versus time. So I've got it labeled. It's 8 points, remember? So 1 point for the title, check. 1 point for the label for each one. Label here, that's label here. So that's 3 out of 8 so far. 1 point each for the units, there. So that's 5 out of 8 so far. And then for the proper scales, scale there, that's 7 out of 8, and my plots there. So 8 out of 8. Good job. 8 out of 8. So now can I describe the motion of the diagram? So let's describe this motion. I see that I am going, first off, I have things that we got to look for, and I want to describe the rate. Is it a constant rate or is it an accelerating rate? Is it going faster or is it going slower? And then I want to see the direction. Is it going away from 0 or towards 0? So positive or negative. So first, is it getting faster, slower, or staying the same pace? Well, I can see that it's going slow here because I have a flat line, and it's increasing in speed. So this shows that it's accelerating. It's going faster. So I'm going to write that down here. Going faster. And is it going away from 0 or towards 0? Well, it's going away from 0, so that's going to make it in a positive direction. So going faster, away from 0. So that makes it a positive direction. So positive direction. Now let's read the next question, number 3. I can find, the goal is to find the instantaneous velocity from a distance versus time graph that shows acceleration. So we have to find an instantaneous velocity. In the test, it's going to ask you, it's going to give you a specific time. Let's find the instantaneous velocity at 3 seconds. So let's make it, find the instantaneous velocity at 3 seconds. Can we do this at 3 seconds? Again, how do I find an instantaneous velocity? Remember, this has been a big thing on all the quizzes. Can I just go to 3 seconds, say, oh, look, 3 seconds seems to be 36 meters, and 36 divided by 3 is going to give me 12 meters per second. Is that what it is going to be? No, I cannot do that. So what do I have to do is I have to find the average speed. I have to find the average speed around 3 seconds. So I take 2 and 4. Now remember, guys, again and again and again, in order to find the instantaneous speed at any given specific time, I have to find the 2 points on either side of that and find the average speed. So how do I do that? Well, I got to go figure out what average speed is. Average speed is going to be my delta distance over my delta time, which means I'm going to have d sub f, or x, is position, minus d sub I over t sub f minus t sub I. Now I'm trying to find it at 3 seconds, so what 2 data points do I use? I use my 2 second data point, and I use my 4 second data point. And I just go up to the table and I find those out. So here it is. Here's my 2 second data point, and here's my 4 second data point. This is my distance. So is that my first or my second one? Well, it's my first one. So that makes it my d sub I. This is my d sub f. This makes my t sub I, my time, and my t sub f. So I'll go ahead and again, I've asked you so many times, write down your variables. So I'm just bring it over here. So d sub f equals 64 meters. D sub I equals 16 meters. T sub f equals 4 seconds, and T sub I equals 2 seconds. So we just plug those in just like you would. What is D sub f? Oh, it's 64 meters. So it's going to equal 64 meters minus, did I change my subtraction sign? No. Minus 16 meters. What was my T sub f? Or have I changed my division bar? No, I keep my division bar. And what about my T sub f? I haven't changed that. That's 4 seconds. And I didn't change my subtraction sign. And my T sub I is 2 seconds. That's how I do it. It's called plugging and chugging. Now I simplify. Equals 64 meters over 2, I apologize, equals 48. Equals 48 meters over 2 seconds equals 24 meters per second. So the speed, the instantaneous speed at 3 seconds is 24 meters per second. It is not going to be the 12 meters per second that we thought. Remember, because this is 36 meters over 3 seconds equals 12 meters per second. Well, that's not it at 3 seconds. That's not it at all. Because look, by the time you reach 3 seconds, you had gone 36 meters. That means you must be going a lot faster than 12 meters per second, because over here you're a lot slower. So again, you have to find the average. Again, so do not confuse that. I'm saying it again. If you want to find the instantaneous speed at a specific point in time, you have to find 2 points on either side of it and find the average speed of those 2 points. So if I wanted to find the average speed for 5, the instantaneous speed for 5, I'd have to take 4 and 6 and do my basically slope equation there. Read number 4. At what time is the car's instantaneous velocity equal to the average speed between 0 and 4? Well, what is 0 and 4 in between? What's the middle point? Well, that'd be 2 seconds. Again, so 0 here. Let's get a different color. Let's use red. So if I'm trying to find the average speed between 0 and 4, remember that's going to be 64. Where is that the average speed at? Dot, 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 dot. Where's the middle point? Well, the middle point is going to be 2. So that's going to give me my instantaneous speed at 2 seconds. So that'd be at 2 seconds. So what is your average speed there? 64 minus 0 is going to be over 2. It's going to be 48 meters per second. Or I'm sorry, 30. Well, 64 divided by 2, I guess, whatever that number is. I can't think off the top of my head. Okay, so at 2 seconds, at what time is the car's instantaneous velocity equal to the average speed between 0 and 4? That'd be 2. Okay, let's go to the next set of questions. Okay, Dan drives his car. His distance versus time graph is below. So you'll be given another one that looks like this. It won't look exactly like this one right here. You'll have another one. So you need to learn all 4 of them. Remember, here are the ones that we've gone over in class. We've gone over if it looks like this. We've gone over if it looks like this. Well, let's make that bigger. So this is there's a couple of those distance versus time graphs. Here's a couple. What is it saying? Is it getting faster or slower? Well, I start off fast and then I end up slower with a flat. So this is getting slower and a positive, slower and positive. This one starts off slow and ends up fast because of the flatness of the angle. So this is getting faster in a positive direction. Let's see some other ones. This is the thing you want to rewind and watch a couple times, okay, just so you make sure you got them. Let's look at these two. This one is slow and fast. So you're getting faster in what direction, though? You're getting faster in a negative direction. I'll take this one. You're flat. Here, you're getting slower in a negative direction. Well, which one does that look like? Well, it looks like this. Those look similar. So, well, we know which one that one's going to be. Let's go do a couple more, though. Let's have a, well, that's constant, so the same as here as it is over there. So it's constant in a, positive direction. Sorry if the handwriting's not so good. And then let's do this one. What is that? That's no movement whatsoever, so it doesn't matter if it's positive or negative. It's no movement whatsoever. So that's 6 of them that we've seen so far. So be able to do those, positive, negative, slowing down, speeding up, be able to feel comfortable with both of those, or all of those varieties. So I have this graph. It's a qualitative graph. Why is it qualitative? Because there's no numbers involved. The last one we did over here, this is a quantitative graph. This is a quantitative graph with numbers in it, so you have to keep that in mind. So Dan drives his car. His distance versus time graph is below. Well, how do I know it's a distance versus time? 1, my unit is meters, and that's distance. And X is standing for position, so please don't forget that. Now remember, this is not saying the axis is not a y-axis, because it's still a y-axis, but it's saying it's position X. Now, can you predict the velocity versus time graph for this acceleration of an object? In order to predict the velocity versus time, you have to know what's happening here. So, let's describe my motion. Before I do the velocity versus time, that's going to be over here. Before I do that, let's describe the motion. Describe my motion includes speed, direction, whether it's constant, slowing, or speeding up. Okay? Well, I can look at it and say it's not constant speed. Agreed? My direction, am I going towards 0 or am I going away from 0? I'm going towards 0, so that's a negative direction. And my speed isn't constant, so I would say it is, look at the angle here. Is that a sharp angle? Yeah. And is this a flat angle? Yes. So it's going from fast to slow. So that would make it it is slowing down in a negative direction. Do we feel comfortable with that? So is it slowing down in a negative direction? Include the speed, the direction, so it's fast and slow, and it's slowing down in a negative direction. Now, how would I draw that in a velocity versus time graph? Remember, this is my positive direction quadrant. This is my negative direction quadrant. So whatever I'm doing, I have to determine which direction is it going. I've already said it's going negative, so it's going to be in the bottom quadrant. Okay. Now, is it going faster or is it going slower? We said it's going slower. That means this is 0 meters per second. This is meters per second. So this is 0 meters per second, say like 4 meters per second, 8 meters per second, 12 meters per second, so on and so forth, right? So the higher you go, the faster you go. Likewise, this would be like negative 4 meters per second, negative 8 meters per second, negative 12 meters per second. So that's just saying I'm going away from my starting point faster. So either way, it's increasing speed. And the further you get down or up from your bar, you're away from you're increasing in your velocity. Well, it tells me I'm slowing down. That means I'm going to a 0. I'm getting closer to a 0. So I'm starting over here and I'm going towards the 0. That's what this graph would look like on a velocity versus time graph. So let's look at this again. This is my graph. It's a distance versus time graph, and this is a velocity versus time graph. Remember, I'm showing you that you have your positive and your negative distance directions or velocities. So feel comfortable being able to describe it and draw the velocity versus time graph from a distance versus time graph. John's bike. Let's go to the next questions. John's bike leaves the malt shop at 0 seconds. His velocity changes at a constant rate from 0 meters per second to 12 meters per second over a 6-second time period. What does this look like? This looks like the period we've been doing the last week. Problems we've been doing this last week of this last period of time. So what does it ask you to do? Well, it asks you to calculate John's acceleration. So how am I going to do that? Well, I need to know the equation for acceleration, which will be on the board, okay? So acceleration is going to equal my delta V over my delta T. Okay, it's my change. And so what is delta velocity? It means change in velocity. It means I have a initial velocity and a final velocity. So it's going to equal my V sub F minus my V sub I over my T sub F minus my t sub I. Are we familiar with this? Make sure we understand this. Well, I need to write down those variables, so let's go read through this again. And I suggest you do the exact same thing when you read the problems on the test. So John's bike leaves the mall shop at 0 seconds. It leaves at 0 seconds. So that's going to be my t sub I. That's my initial time, right? Its velocity changes at a constant rate from, so my beginning at, that makes my v sub I, my beginning or initial velocity at 0 meters per second to a final velocity at v sub f to 12 meters per second. And it took 6 seconds to do that. So that's going to be my t sub f. Look, I have all my variables, but let's make sure I have this down. So I'm going to write down these variables first. V sub f, v sub I, t sub f. Well, let's make it so we can see this better. V sub f, v sub I, t sub f, t sub I. V sub f equals 12 meters per second. V sub I equals 0 meters per second. Now, this is important that you need to note it's 0 meters per second for velocity. It's not a position. If it was just a distance or position, it'd be 12 meters or 0 meters. It's velocity. So that means it's getting a faster velocity. And your t sub f equals 6 seconds, and your t sub I equals 0 seconds. Now let's just plug and chug. Come down over here. It's going to equal 12 meters per second minus 0 meters per second over 6 meters per second minus 0 meters per second. And that's going to get you simply, now make sure you remember all this, guys. It's going to get you 2 meters per second squared. Let's not forget that, please. 2 meters per second squared. That is my acceleration. Now, what are the points for? You get 1 point for the equation and your variables. So if you don't have that, you lose your point. You get another point for solving it. So I got 2, that's the correct answer, and I got another point for my units. Please do not forget your units. So now it comes over here and it wants me then to make a quantitative graph. So use the above info from John's trip to create a quantitative velocity versus time. What kind of graph is that? It's a very specific velocity versus time graph. Well, what's the first step into always making a graph? Create a data table. So I got a data table. Let me create it. It's going to be my time is my x, right? It's going to be going on my x-axis. So time is going to be on my left side. So time in seconds. And it's going to be velocity is my y-axis. So velocity in meters per second is my velocity, right? Now I'm going to have 0 seconds, 1 second, 2 second, 3 second, 4 seconds. And of course, it's going to be, it's going up 2 meters per second squared, right? So the first one is 0 meters per second squared. But at 1 second, meters per second, it's going up 2 meters per second squared. So for every 1 second, I'm increasing 1 or 2 meters per second, right? So 2 meters per second here, and then increase 2 meters per second again, so that's 4 meters per second. Increase by 2, that's 6 meters per second. This is going to be 8 meters per second. And I'm running out of room, so let me real quickly come over here and continue over on this. 5 meters per second, or 5 seconds, 6 seconds, 7 seconds. It's going to get me 10 meters per second. This is going to get me 12 meters per second. And it's going to get me 14 meters per second. Now, if you look over here, this is the one that we found the data for, right? So we shouldn't be surprised on that. But let's just go up to 6 seconds and see how we do. So let's create a little graph over here. Let's use this magenta color. Oh, that line's crooked. Okay, so it's going to be the effect of time on velocity should be the title of our graph. So the effect of time on velocity. And let's go, it's going up by 2. So let's go 0, 2, 4, 6, 8, 10, 12, 14, 16. Now, what is it going? It's 2, 4, 6, what? It's velocity in meters per second, right? So it's going to be velocity is my y, and meters per second. And this is time, agreed? So time, I'll put it out to the side over here. Anyway, let's go 1, 2, 3, 4, 5, 6, 7, so on and so forth. So let's get over here, time in seconds. That's going to be labeled. And then let's go do our points. So at 0, 0, let's use a different color here so we can see this, so we can see the contrast. So 0 there, and then 1 to 2 meters per second, and then 2 to 4 meters per second, and 3 to 6 meters per second, and then 4 to 8 meters per second, then 5 to 10 meters per second, 6 to 12 meters per second, and then 7 to 14 meters per second. Okay, that's a constant acceleration. That's a pretty acceleration graph. It's a constant acceleration. This is not a distance versus time graph. This is a velocity versus time graph. This is not showing my position. It's showing the speed. It means I'm getting a constant speed. Now let's check to see, do I got a title? Check. Do I have my labels for both? Check and check. Do I have my units for both? Check, check. Do I have my proper scaling? Yes and yes. And do I have my points? Yes. So it's going to be 8 out of 8 again. That's what the graphs are for. So 8 points for that. So did I use the above info from John's trip to create a quantitative velocity versus time graph? Yes, I did. So the next one. So if John continues on his acceleration, how fast will he be traveling in 12 seconds? Now it's asking for velocity. Now remember, this is the equation. A equals V over T. What's my A? First things first, let's write down our variables. A equals T equals, and I don't know V, equals question mark. This is the guess method, right? My acceleration was 2 meters per second squared. My time was 12 seconds squared from the problem. And I don't know my velocity. So let's plug it in. 2 meters per second squared equals V over 12 seconds. So what do? I do the order of operations. I isolate my variable. So times 12 seconds on one side and times 12 seconds on the other. A second is going to be left out. I'm going to be left with 24 meters for every 1 second. It's going to be my velocity. There it is. Be able to do that. Moving on. A police officer speeds up to collide with a runaway car using a new tire stop machine to stop the car. Now this is a real thing. They've got like a front end loader or front loader on trucks now, and it has a rope contraption that when you drive up, you drive up behind the person's driver's side back tire, and once you get underneath it, it automatically it pulls it in and wraps around the rope and makes it wrap around the axle, so the axle can't go, or they can't go anymore. So that's pretty cool. So I don't think it really exists. So this is a highway patrol or a cop car going after a runaway car, right? It's driving really fast and they're trying to get to so it doesn't go off a bridge or something. So it's going, and now it's going at a constant rate. Hopefully you can see that. Do you see that the line doesn't change ever at all? It's the same. If you hold a pencil up to it, you'll see that it doesn't ever change. It's the same angle, same angle, same angle. While this one, lower angle, higher, 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 higher. So this is getting a faster speed. This is getting faster. Remember, from the example earlier, scroll back and go back to the earlier time. If this is lower and this is higher, that makes this faster, going faster in a positive direction. So now let me know what's going on. And they're going to collide, aren't they? They're going to collide. So the question says, Describe the motion of the officer and the runaway car. Include direction, initial position, amount of time, constant, increasing, or decreasing speed. All those things. So the officer, what direction is it going? Well, we can definitively say that it's going faster. So let's do, the officer is going faster. Or direction, I'm sorry. Direction, it's going in a positive direction. In a positive direction. Its initial position is at the 0 mark, right? This is a distance versus time. You see this x over m? That's a distance over time. So its initial position is 0 meters. Its amount of time it took 8 seconds to go from 0 meters to 70. So it took 8 seconds to go from 0 meters to 70 seconds. So it's the amount of time is 8 total seconds. 8 seconds. And then is it increasing or decreasing or staying constant speed? Much faster. Getting much faster. Getting faster. Let's look at the runaway car. What direction? Again, it's going away from 0 in a positive direction. So the direction's still the same. Positive direction. Let's get this blue. It is also going in a positive direction. Now, what is its initial position? And this is something that people keep messing up on the last test. Where does it begin at time 0? This is time 0. Make no mistake, guys. Time 0. Time in seconds, 0 time. So at the 0 initial time, it was 30 meters. 30 meters away from the cop car, okay? So initial position is 30 meters. Do not mess that up on the test. How long did it take to go before it collided? Again, it took 8 seconds. So the time is still the same, 8 seconds. But I want you to notice something. It went from 0 to 70 in 8 seconds. I apologize again, I did it. It went from 30 meters to 70 meters in 8 seconds. That's only 40 meters. This one went from 0 to 70, so that's 70 meters in the same amount of time. So which one had a higher average speed? Well, this one, obviously, because if we were to make that little line there, you'll see that's a much steeper line than the other one. But that's neither here nor there. Let's get back to the topic at hand. So this one went 70 meters in 8 seconds. This one went 40 meters in 8 seconds. By the end of it, let's go back to describe this real quick, though. And is the speed the same, constant? It's constant increasing. It's a constant speed. Constant speed. I can say this one is a constant acceleration. Again, what does acceleration mean? Acceleration means, are you changing your velocity? It is constantly changing its velocity. This one is constantly keeping the same velocity. Remember, we worked on those words in the class. We wrote those definitions on the board, so let's not forget those. So the question asks, which car has the highest instantaneous velocity at 8 seconds? At 8 seconds. How do I do that? Well, I just look at the angle. Let's compare these two angles together. So let's zoom in. This angle versus this angle. Which one's a higher degree? Well, this one's higher. So which one's going faster at the time of collision? Well, the cop car is going faster at the time of collision. So which car has the highest instantaneous velocity at 8 seconds? Well, 8 seconds is where they collide at. So it'd be cop car. Explain. It has a higher slope at 8 seconds. That's the answer. Is that a sharper angle, a higher slope? Okay, let's go. So there's that. Now it says, at what position does the officer contact the runaway car? Explain. Well, you tell me. At what position here? Distance. Well, we draw a little line here. We see it's roughly ... 70 meters. So for the question, it's at what position, and explain. It comes into contact with the car at, let's use a different color. Comes into contact at 70 meters. Comes into contact at 70 meters. Explain. That's when the two lines intersect. That's when the two lines, no, you can't write two lines on a paper because you have to put it in the, so let's do this. When the two lines intersect. Intersect. Okay. Okay, so here's one of the really last hard math problems. What is the total distance traveled by a greyhound if it accelerates at the rate of 5 meters per second for 7 seconds? Okay. What is this question asking me? It's asking for distance, and it gives me velocity. I apologize. It gives me acceleration, time, and, well, I'm sorry. It doesn't actually. It only gives me velocity. So I was right. It only gives me velocity. Actually, no. That's a typo. It was supposed to be 5 meters per second squared. That's a typo. That's supposed to be 5 meters per second squared. So it gives me acceleration. It gives me acceleration, and it gives me time. So let's solve this. This is the equation. D equals V sub I times T plus 1/2 A times T squared. Now, what variables do I have? I have acceleration, I have time, but I do not have velocity. What's my initial velocity? We assume the initial velocity is going to equal 0 meters per second. It starts at a rate of 5 meters per second for 7 seconds. So assume your initial velocity is 0. Your acceleration is going to be 5 meters per second squared. Again, I'm messed up on that one. And then your time is going to equal 7 seconds. So we've got our variables. Let's plug them in. So it's going to equal, what's my V sub I? So D equals, V sub I is 0 meters per second times 7 seconds. Take care of that first. Plus 1/2 and 1/2 A, so that's 1/2 5 meters per second squared times my T squared, which is 7 seconds. 7 seconds squared. Remember, do not put 7 seconds squared. I actually almost just did that after I warned you. Now, what is it saying that I need to do? Let's bring each one of these down. It's saying now it's going to be 49 seconds squared times 1/2 5 meters per second squared. So that's going to give me 2.5 meters per second squared. 2.5 meters per second squared. A positive, by the way, a positive 2.5 meters per second plus, well, 0 times 7 is 0 meters. And why? Because remember, meters over S times an S is going to cross out my S's and give me 0 meters. Next, I need to figure out what 2.5 times 49 is going to equal. So 2.5 times 49 is going to give me 122.5 meters. 122.5 meters per second. or I apologize, just meters, because the second squared is times the meter over a second squared times the second squared is going to cross out my second squared, so it's going to give me plus 122.5 meters, and plus the 0 meters down here. So what's my total distance? Equals 0 meters plus 122.5 meters equals 122.5 meters. So 122.5 meters. Okay, what are the points for? My equation and my variables, my final answer, and my final unit. 3 out of 3. Okay. Now let's get to the end of this. I need you to tell me the effective time on position of a cat chasing a laser pointer going back and forth. The one that we did in class today was an example of a fish swimming back and forth. So this doesn't really matter. It's the same thing as that this is my starting point, and something keeps, like this is the starting point right here, like this is the 0 point, and something keeps going away from my 0 point, then turns around and goes towards my 0 point, and turns around and goes towards my 0 point. That's what this is looking at. If you flip that sideways, it kind of looks like that. Okay, so let's see what the questions are asking then. So again, this is traveling. It's traveling away from 0, then back towards 0, then away from 0 and a negative, away from 0, then towards 0, and away from, so on and so forth, right? It asks, at what time interval was the cat slowing down in a negative direction? In a negative direction was it slowing down? Well, again, if it's going away from 0 is a negative direction, or going towards 0 in a negative, I apologize, again. So going in a negative direction is going towards 0. So where is it going towards 0 at? So it's going towards 0 here, and it's going towards 0 here. Okay? At what point in time is it kind of slowing down towards there? Well, this is kind of constant, and this one is actually speeding up, if anything. So we could say there's none. There's not a single one. Now the question that's going to be asked you is going to, I've changed them up, right? What I did is I went through the test and I wrote it down in a different format and a different kind of question, the same kind of question, but I put it in a different way. So another one might ask, at what time interval is the object slowing down in a positive direction, right? So positive, it's slowing down in a positive direction. Well, this one is slowing down there at the A to B. It's slowing down there. But okay, so that's what it's going to ask you. Don't worry that this one doesn't have a good answer right here, because at what point in time is it slowing down? Is it slowing in, again, this, if it goes towards 0, if it's going towards 0, it is a negative direction. Okay, this is towards 0. That's negative. This is towards 0. That's negative. Even though it's down here, it's going towards 0, so it's going in a positive incline, right? This is not a velocity versus time graph. This is a distance versus time graph. So anytime it's angled up, that's a positive direction. So it is, and it's not slowing down on either one of these. Look at these. It's not slowing down either way. So I'd put none of them. The next one, at what time interval was the cat speeding up in a positive direction? Speeding up. Positive means going away from 0. Okay? So this is negative, right? Because it's going towards 0. Negative because it's going towards 0. This is negative because it's going towards 0. At what time was it speeding up in a positive direction? Well, this was going away from 0. So let's look at this again. Is this going away from 0? Yes. Is this going away? Away from 0, so it is positive. This is going towards 0, so it's negative. This is going away from 0, so it's also positive. And this is going towards 0, so it's negative. And this, okay, if you look, though, it's sharp here, flat there. Sharp here, flat there. Again, none of them are actually speeding up. They're all actually getting slower. So I'd put none here, because it's not happening. And then number 15 is, at what time is the cat not moving? At what position, I guess? Let's call it times. What times is the cat not moving? Give me the letters that represent the cat's not moving. Okay, here it stopped, no movement here, and then no movement here. So B and E. B and E, the cat is not moving. Now, the questions on the test will be multiple choice, and you'll have an option. So don't worry about that one. So on the test, you will have an option. Finally, the last question that we're doing. Let's look at this right here. This is what our graphs. Remember, we did the little car roller. So it went from 0 to position X. So you're going away from 0. What direction is it away from 0? Automatically, it's positive, correct? So if it's going away from 0, it's positive. You might have it the other way, and it might be going negative. Just know that if you're going away from 0, it's positive, and towards 0 is negative. So let's draw these on a distance versus time and a velocity versus time. Create a qualitative, so no numbers, position versus time graph for the car, this little car right here. Well, remember, what happens the moment it leaves my hand? It's going uphill. The moment it leaves my hand, my acceleration is going to be going the opposite direction. So my motion diagram is, let's draw a motion diagram for this. Okay, is it going to go faster or slower? The only force acting on this car once it leaves your hand or once it stops being propelled by another force is gravity. And gravity is working towards it, or against it, I apologize. So you start off fastest, then you slow down, and stop, basically. Stop, and then you start rolling back the other way, right? So, but before that happens, say it gets to right here. What's its distance versus time? Is it going away from 0? Is it getting faster or slower? It's getting slower in a positive direction. So what do we need to do? We need to draw showing that faster first, so a high angle, and then a low angle there, and you need to connect them. So there it is. There's my distance versus time. It's in a positive direction, and it's slowing down. Perfect. Let's go to this next one. Let's use... Now, what's a velocity versus time? Is it going in a positive direction? Yes or no? Yes, it's going in a positive direction. So what's happening to it? What do I need to draw on here? I need to simply draw which quadrant is positive and which quadrant is negative. Well, this is my positive quadrant, and this is my negative quadrant. What direction? It's positive, so it has to be in this quadrant. Is it getting faster or slower? It's getting slower. Again, this is 0 meters per second. So how am I going to draw this? It's going slower towards 0 meters per second. So there it is. That's simple. Now let's describe these. Is this describing velocity? This graph right here, is it describing velocity or acceleration? Is this thing velocity or acceleration? It's distance over time. That's velocity. Okay. What is the direction? We already said it's positive. This one is this describing velocity or acceleration again? Well, it's describing acceleration, because acceleration is velocity over time. Now remember, velocity is the rate of distance over time, and acceleration is the rate of velocity over time. So if my axes include velocity and time, then it's acceleration. So it's going to be acceleration, and it's positive direction. It's positive direction again. Okay, I hope that helps everybody here. There's no confusion. I hope we all feel good on this. So